In this video, we're going to do a concrete example where we're going to compute the surface area for some surface. So let's first try to understand, what is this surface that we are asked to compute the surface area of? So the actual surface itself is this x squared plus y squared equal to 4, which, because we're living in 3 dimensions, we're having a surface in x, y, z, is just the equation of a cylinder. And then I have some constraints. This has to be only the portion of that cylinder between z equal to 0 and z equal to 16 minus 2x. So I can try to visualize this. Let me put up some axes here. So I've got the x, y, and z axis. Well, x squared plus y squared equal to 4 is the equation of a circle if it's down in the xy plane. So I'm going to draw that circle down here first. So that's the circle at the z equal to 0, the lower bound for my plane. But it's going to go up until I hit z is 16 minus 2x. And z equal to 16 minus 2x, that's the equation of some plane. It's going to look a little bit like the line z equal to 16 minus 2x, but then for all values of y. And so what happens when I try to form this cylinder is it looks a little something like this. It looks like a cylinder with a bottom cut off at the xy plane, but then sliced a little bit because of this plane z equal to 16 minus 2x. Now, when we looked at a couple different formulas previously for describing the surface area of a surface, we noticed that there was times when you might want to describe it parametrically or explicitly or implicitly, which just sort of depend on the surface. Now, because I have this symmetry with the x squared plus y squared equal to 4, which gives the equation of a circle, it sure seems like there's going to be some symmetry that we can take advantage of by using a parametrization. So the formula I'm going to use is the parametric one, and I'll recall for you that it is the double integral over some region in the parameter space of the length of RU cross RV du dv, where u and v are your parameters for your position function r. And so this is the formula that we're going to use. And thus, the real key to being able to do this effectively is all about coming up with that parameterization. If I know what that position function r in terms of the parameters u and v are, then I can just plug it into the formula. It's just a computation at that point. So what's a good choice here for my u and my v? Well, it's certainly a cylinder. And the cylinder just screams, be inspired by cylindrical coordinates. But the point is, cylindrical coordinates has 3 different components. There's an r, there's a theta, and then there's a z. So a height, if you will, above the plane, where the plane is described in polar coordinates in terms of r and theta. So I want to set my parameters to be 2 of those 3 possible choices, the r, the theta, and the z. Indeed, in our previous video of those 3, we chose r and theta as the pair that we're going to do. Now, in this video, the object that we are studying is not the plane, it's the cylinder. The cylinder is the thing that I'm interested in studying. And the cylinder always has a fixed radius. Because of the x squared plus y squared equal to 4, or 2 squared, this has a radius of 2. So it wouldn't make sense for me to use r and theta as parameters. Because, well, if you have an r and a theta, well, what's your z? You don't know. And you always know your r. R is not changing. R is equal to 2. So I'm going to make my parameters theta and z. Specifically, I'm going to say that my position function r is a function of theta and z. And let's see how we can do this. I need to specify the x, y, and z components of it. So the x component of it, well, standard polar coordinates tell you it's r cosine of theta. R is 2 here, so I'll write 2 cosine of theta. The standard y component in polar coordinates, say, is r sine theta. R is 2 again, so 2 sine of theta. And then finally, the z component, well, is just z. The height is my other variable that I have, z. So now I need to compute out the cross product, which is in my integrand. So let me try and do that. I'm going to go all the way up here. I'm going to say that r theta is going to be the partial with respect to the first variable. Theta is going to be minus 2 sine of theta, 2 cosine of theta, and 0. And then finally, rz is going to be, well, no z in the first component, so just 0, 0, and then 1. I need to then do the cross product of these 2 things, so that's r theta cross rz. This is given as a determinant. And in our determinant, we're going to put in an I hat, a j hat, and a k hat. We'll do our r theta line first, so minus 2 sine theta, copy and paste, 2 cosine of theta, copy and paste, and 0, and then 0, 0, 1. So what do we get? There's going to be an I hat component, and that's going to be multiplied by 2 cosine of theta. There's going to be a minus j hat, which is going to have another minus sign, so it's going to be a plus j hat, and then 2 sine of theta. And then no k hat. Maybe I'll just put it explicitly 0 times k hat, just so it's clear. Final thing I need to do until I get my integrand is the length of this, so r theta cross rz, which is square root of the sum of the components squared, so 4 cos squared plus 4 sine squared. Cos squared and sine squared is 1, so square root of 4. In other words, it's just going to be 2. Okay, great. So now we know what that integrand is. It's just the value of 2. So if I'm going to come all the way up to take a look at what the formula was I was trying to plug in, it was this double integral over the region of the cross product, the length of this cross product. We just figured out that's 2 and then du dv. Okay, so I'm going to plug in that formula now. So my surface area is going to be a double integral, and the hard part is going to be figuring out the limits of integration. The 2 is going to be easy. And then I have to write out either d theta dz or dz d theta. I don't know which direction is going to be better. Sometimes when you switch the order of integration, it's easier to do one way than the other. I'm going to assert the answer, just because I know what it's going to be, is dz d theta, but I'll come back and figure out why I chose that way and not the other way in a moment. So if I do it this way, what was the z between? The z was between 0 and, if I remember correctly, 16 minus 2x. Okay. But 16 minus 2x, I don't want to write it in terms of x, I wanted to write it in terms of theta and z. So, well, x is 2 cosine of theta, the radius times cosine of theta. So this is really 16 minus 4 cosine of theta. That's the upper limit in the z component. And then theta was 1 full revolution around the circle, so 0 to 2 pi. And then now I can see why I chose this particular order, because if I do the integral with respect to z first, I'll get something in terms of theta, and then I can integrate that with respect to theta and I'll get my value. Okay, so let's try it. I'll leave the 0 to 2 pi, the outside, and not touch it. And then for the inner integral, well, the integral of 2 is just 2z, but I need to evaluate it, my limits. So it's 2 times 16 minus 4 cosine of theta minus 2 times 0, I won't write that. And then all of this integrated out with respect to theta. This is all very nice. I have a 2 times a 16, which is going to be a 32. That's going to get multiplied by the 2 pi and become a 64 pi. Then I'm integrating cosine over its entire period, which I know is going to be 0. So actually, that's it. Final answer. All right, so that's the surface area for this particular region. And I really want to emphasize that the most important part of all of this was coming up with the parametrization and trying to draw out the region and really think what parameters make sense. And in this case, when we have a cylinder where the radius is fixed, you don't want to use the radius as one of your parameters. So theta and z as parameters made a lot of sense here.